Hi, this is Christina with Dojo Research and Consulting, and today I will be showing you how to set up a two-dimensional pot boiling simulation using COMSOL Multiphysics. We'll begin by opening COMSOL Multiphysics 5.3. Selecting the Model Wizard will walk you through the basic setup of your simulation, and we're setting up a two-dimensional simulation in the interest of saving computational resources and also for demonstration purposes. The list of available physics shown in this window are displayed based on which modules you as a user have access to. To follow along with this tutorial, you will need access to the CFD module and to the heat transfer module. One nice feature here in the wizard is that you can select the interfaces that you need, and COMSOL will automatically include the individual physics interfaces and also the interfaces used for coupling between physics. In this tutorial, we have three sets of equations going on: those associated with laminar flow, those associated with the liquid-vapor interface tracking, and those associated with heat transfer. For interface tracking, we're going to be making use of the phase field interface. There are obviously several other physics options for multiphase flow provided by COMSOL, but we're going to stick with phase field for this particular tutorial. And we select this interface by going to Fluid Flow, Multiphase Flow, two-phase flow phase field, and selecting laminar, and click Add. For heat transfer, we're going to select non-isothermal laminar flow, which will provide us with the heat transfer and physics interface and the multiphysics coupling interface. So we find that by collapsing the multiphase flow and going to non-isothermal flow and selecting laminar flow. And you can see that COMSOL has populated all of the physics interfaces we've selected and the ones we haven't selected but we need. Right here, the coupling interfaces. And before we move on, we need to delete this second laminar flow interface. It's redundant and we don't need it. So click Study. We'll be selecting a transient study for this simulation because we're interested in the creation and movement of bubbles over time. And once we click Done, COMSOL will open a new MPH file with the physics interfaces and study settings that we've selected in the Model Wizard. Before we begin setting up our simulation, I want to roadmap our steps so that you know where we're going. First, we're going to import our relevant global parameters here, and then we'll import our variable definitions local to component 1, and then we'll set up our geometry, and then we'll set up our boundary and initial conditions for the physics interfaces, and we'll do the same thing for the multiphysics coupling interfaces here. Then we'll set up the mesh for our domains, our study settings, and then we'll run the study, and then we'll take a look at some results. So first things first, let's import our global parameters. You could enter these manually, but we're going to import them. And then we'll do the same thing for our local variable definitions. And now that we have our parameters and variables, we can set up our geometry. So first things first, we're going to create a rectangle with a width of 50 millimeters and a height of 50 millimeters as well. I could also enter those as millimeters themselves by just including the unit in brackets afterward. COMSOL takes care of all that on the back end, which is nice. We want the base to be at the origin, so this setting is good. And let's hit build and take a look. Yeah, so this is the square that we wanted, and we want to introduce, we want to split this in two so that we have a domain for our liquid and then a domain on the top for our vapor. And an easy way to do that is to introduce a layer by opening up this layer menu, and we can specify the thickness to be 25 millimeters and select layer on the bottom. We could also select layer on the top. since we're going to be splitting it down the middle. So let's click Build All Objects, and you can see that now it's a square that's been split in two. Next, we're going to draw a polygon that's going to serve as the structure for the first cavity where the vapor bubbles are generated. And this cavity can kind of be thought of as a sort of like artificial nucleation site. And we're going to have three of them. We're going to build the first one from scratch, and then we'll just copy the second two. So the way we do that is by right-clicking Geometry and selecting Polygon. COMSOL has a couple different ways for you to import the coordinates for the vertices of the polygon, and I'm going to import a text file that has these coordinates. Let's click Build All Objects, and now you can see the polygon down at the bottom of the liquid domain. And this is great, but next we're going to want to add a liquid vapor interface, which will be, this will serve as the vapor bubble at the bottom of the cavity. And to do that, we're going to create a circle with a radius of 3 millimeters. Whoops. And we want the base to be located here. Let's take a look. Right, okay. So this is, the inside of the polygon looks great. This is exactly what we want. You can see, you can kind of imagine this is going to be our vapor bubble, and then this little domain here will also be liquid, same as this. However, we have this domain on the outside that we kind of want to cut away. So the way we do that is by adding a Boolean feature called compose. And the polygon and the circle are our input objects. And the formula here is the polygon and then the polygon and the circle. And these expressions, as you see over here, come from, they're the names of these features. And we obviously want to keep the interior boundaries, or else why did we do this? So this looks good, so let's take a look. Right, so now it's cut away, and this looks more like what we were expecting. So now we're ready to copy it. So the way you can copy a feature is by right-clicking Geometry, going to Transforms, selecting Copy. We want our cavity to be the input object. We want to keep the input object, otherwise we're copying something only to delete it, which we don't want to do. And we want our X displacement to be 15 millimeters. And we don't want any Y displacement because we want it to stay on this bottom line at the bottom of the pot. Let's click Build. Okay. And we're going to copy one more time. Input object, let's keep copying the original. We could copy the copy, doesn't really matter, but then we also want to make sure that if we're going to copy the original, we want the displacement to be twice as far. Okay, so now we have our geometry all set up and ready to go, and we're ready to move on. Before we get started on setting up our physics interfaces, we have some stabilization settings we'll need to adjust. And in order to actually see those settings, we need to click on this eye icon and make sure that stabilization is selected. So first physics interface we're going to take a look at is the laminar flow interface. And let's start by adjusting a few settings in the physical model. So we have incompressible flow, no turbulence model selected since it's laminar flow, and we want to make sure we're including gravity. And we want our reference position to be at the bottom of the pot, which is exactly what it is by default, so we'll leave that there. And as far as stabilization goes, we're going to make sure that the consistent stabilization options are unchecked, and the inconsistent stabilization options are checked. And we only need to add one boundary condition that isn't already included, which is an outlet. So let's do that now by right-clicking and selecting outlet. And while we're here, let's go ahead and select the boundary that is going to be our outlet, which is this, which is like the top of the pot. And we're going to leave that as a pressure boundary condition and leave these settings as they are by default. And everything else is good as it is. We'll check on the walls, make sure that they're all selected. The internal boundaries, we don't have any boundaries for those as far as laminar flow is concerned, so that's fine. Yep, and you see our gravitational acceleration, and we're good. So now we can move on to the phase field interface. The only things we'll be changing here are these two parameters. So we're going to be changing the interface thickness parameter to be 4 to the minus 4 meters and the mobility tuning parameter to be 10. And next we're going to be setting up our initial values. We actually need to have two. So we have one by default, so let's add our second one. And the reason why we need to have two is because we need to specify which domains are liquid and which domains are vapor initially. So let's start with initial values 2 and select the domains that we initially want to be considered vapor, which are these. And then we want to select fluid 1, so phi equals -1. So that's how we're telling COMSOL we want these domains to be considered vapor initially. And now if we go back to initial values 1, you can see that the domains we selected in initial values 2 have been overridden, so the only domains left are the ones that we want to be considered liquid, so we don't have to change anything as far as domain selection is concerned. So the only thing left here is to select fluid 2, which is already selected for us, phi equals 1. The wetted wall boundary is fine. There's actually a boundary here at the top, which we know already is an outlet, so let's add our outlet boundary condition. Right-clicking phase field, selecting outlet, and then just clicking on this boundary. Now if we go back to the wetted wall boundary, you can see that now the top boundary is no longer selected. Next, we need to specify the initial liquid-vapor interfaces, and the way that we do that is by right-clicking phase field and selecting initial interface. And we'll select the boundaries located within the cavities and also within the pot itself. Now the last thing we'll need to finish off the phase field interface is a weak contribution, which just involves adding a source term in the weak form of the phase field equation. An explanation of the weak form in finite element analysis is well beyond the scope of this simple tutorial, so I'll link here to a nice introductory COMSOL blog. Now to be able to add a weak form contribution, we'll need to click on the icon with the eye and make sure that the advanced physics option is checked, which it is for me already. And now we can go down to the phase field interface and right click, and go to more and select weak contribution. All of our domains should be selected. And here is what the expression for the weak expression looks like. You'll note that the expressions for phi source and u source are just the source terms for the conservation equations, and you can find the expressions for these under variables right here. And now we are done with the phase field interface, and now we can move on to the heat transfer interface. So this interface has 3 default conditions. We're not going to be using this boundary condition, but we'll just leave it there. Other boundary conditions will come and override them, so we don't actually have to delete it. And we're going to be adding several additional boundary conditions, but first we need to change some of the interface settings. So we'll select heat transfer and fluids, and we'll select surface to surface radiation and scroll down to the stabilization settings. And we will uncheck streamline diffusion and also make sure the isotropic diffusion is selected. Then we will move on to fluid 1 settings. And we're going to scroll down to thermal conductivity here. And instead of having be from material, we're going to have it be user defined, and we're going to define it as this expression. This variable expression is also given up here, and we're going to set the, scroll down a little bit, the fluid density to be user defined as well. And we want this to be pulled from the two-phase flow interface. So we specify it in that way. And the heat capacity at constant pressure to be user defined, C sub P, and we will define the ratio of specific heats to be unity, which it is right there. Next, we're going to set the initial condition everywhere to be the saturation temperature. And we're going to create the following boundary conditions all at once, and then we'll go through them at the same time. So right-click heat transfer and fluids, and we're going to add an outflow. We're going to add a heat source, and we're going to add 2 heat flux boundary conditions. For the outflow, we just need to select this top boundary. Again, that's all we have to do. So that one's done. The heat source term is representing the source term in the energy equation, so we select that to be applicable to all domains. And the expression is user defined, and we're setting it to Q sub S. The first heat flux expression is the convective heat flux, and we will set that heat transfer coefficient to be 10 watts per meter squared Kelvin, and the external temperature to be Tsat. Oops. And we want this to be applicable to these walls. Good. And our next heat flux is the heat flux applied at the cavities, which is actually responsible for the bubble creation. So this expression is going to be given by Q, which we define in our variables. And this is going to be on each of the outer surfaces of the 3 cavities. Okay. Last but not least, we need to right-click again and select diffuse surface for our domains. We need to make sure that including surface radiation is selected. The radiation direction is going to be positive normal. We'll leave the ambient temperature at it as is. Include diffuse irradiance set to 0, good. And we'll set the surface emissivity to be 1. Now the last thing we have to do is select our boundaries, which again is all of the boundaries that the heat flux for the cavities applies to. Lots of clicking. And that's all we need for the physics interface. So we're all done with our individual physics interfaces, and now we can move on to the multiphysics interfaces. First, we'll take a look at the two-phase flow phase field settings. And instead of setting up the material properties in the materials section of the component, we can do that here. So fluid 1 is our vapor, which we specified in the phase field interface. So we're going to set the density to be user-defined, and we want it to be rho sub v. The expression for that is specified under variables right here, which is just the ideal gas law. And for viscosity, we're going to set it to be user-defined, and we're going to define it to 4e to the minus 5 Pascal seconds. And then fluid 2 is our liquid, so we'll set that to be user-defined, and we'll set that to be rho sub L, which is just equal to 1,000 kilograms per meter cubed, which we specified up here in parameters, right here. And finally, the dynamic viscosity, we are going to set to be 1e to the minus 3 Pascal seconds, and we're going to specify the surface tension coefficient to be user-defined. 0.0588. And the last thing we have to do here is to just make sure that for fluid flow, the laminar flow interface is selected, and for the interface, the phase field interface is selected. There's no other options here, so we kind of don't have to check it, but if you're setting up a more complicated simulation, it's always good to double check. So we're done with that, and we can move on to non-isothermal flow. There isn't much to do here. We just have to make sure that all of the correct interfaces are selected. So density is fine from the heat transfer interface, and similarly for the coupled interfaces, these both look fine. And now that all of the physics settings are completed, we can move on to the mesh. Now for the mesh, we're just going to keep it really simple. You can obviously refine this to your taste. I just want to set up a mesh that's good enough to get us some results that we can look at. We're going to take the physics controlled mesh and change the setting, element size setting to be finer, and choose build all. That looks fine. And that's all we're going to do for this one. There's obviously a lot of things you can do with the mesh, but like I said, we're just going to keep it really simple. And now we can move on to the study. For the study, we are going to keep it simple and keep everything as it is by default, except we're going to change the time steps under step 2 of the study, so we don't have to do anything for the phase initialization. That's all fine. But for the time-dependent part, we're going to change the time step itself to be 0.01 seconds. And just note that this is not the time step size that the solver takes as it's coming to a solution. That's controlled by the solver itself. This is just the time step that the solver will output results for us to look at. And then we're going to have it run from 0 seconds to 2 seconds. You can set up results to look at while it's solving, but we're not going to do that. And before we hit compute, I just want to note that multi-phase flow is pretty computationally expensive, so this is going to take a bit of time. I think it takes about 40 minutes on my machine. So just be patient, take a coffee break, and come back when it's done. My simulation is finished, and now we can take a look at some other results. If you go to the results tree here, you can see that there are some variables that are plotted by default. So let's start with velocity first. You can see that by default the last time step is shown, but if you go here you can look at any of the time steps that the solver has saved data for. So let's take a look at 1/10 of a second. And you can see that the bubbles are just starting to form here. And we're looking at a velocity plot, so this isn't super interesting to look at because we created this tutorial to show bubbles boiling in a sort of pot scenario. So let's take a look at the volume fraction. And this looks more like what we would expect. Red on this plot corresponds to vapor and the blue corresponds to liquid. So COMSOL has a nice feature where instead of just looking at static pictures, you can create animations. So to do that, you come up to this little movie reel icon and select player, which allows you to view the animation within the COMSOL environment. You could export it automatically to a file, or you could export it to a file later after looking at it in the player. So as you can see, let's press play again. It happened so quickly. It shows, by default, it shows each frame for 1/10 of a second, so the bubbles go pretty fast. So let's slow down so we can maybe get a better look at the bubbles being created. So let's display each frame for 1 second. This is going to make it pretty choppy, but it'll, allow us to look at more of the frames. You can also look at other default variables, such as temperature, isothermal contours. You can also create your own plots. So you do that by right-clicking on results and choosing 2D plot group, and then going down to the new plot group and right-clicking and choosing surface. You could also choose any of these other options, but let's just go with surface. And you can see here that by default they give you the velocity variable, but if you go and click this option, it will let you browse through the variables that are available that you could plot. So let's go to component and phase field, and let's plot the phase field variable, and then select plot. And now you can see the phase field variable for I guess this is 2 seconds, but we could go back up and select whatever time we'd like, etc. So this tutorial has just been a glimpse of an example of a simulation you could set up in COMSOL, particularly one involving coupled physics. I hope you've enjoyed it, and thank you for watching.